Hey guys, welcome to day 11. Today we're going to kind of cover two sections in one, although we're not going to get all the way through Lewis structures. Section 9 is pretty simple. You have been dealing with the localized electron model really since Chem 1. It's this idea that a bond is a shared pair of electrons, or a double bond is two shared pairs of electrons. The other kind of competing theory with the localized electron model is this molecular bonding or molecular orbital theory, which we will talk a little bit about next chapter. Molecular orbital theory basically says that these electrons belong to the whole molecule, whereas the localized electron model says that these electrons are shared between two adjacent atoms. Okay, so pretty much whatever you see here in the Lewis structures, the simple structures that I do have, kind of demonstrate the localized electron model. Now, we know that there's a couple major types of bonds. There's ionic bonds in which electrons are transferred, but our focus here is going to be more on our covalent bonding, which is a shared valence electrons. It could be two shared electrons, four, or even six shared electrons. So there are something called lone pairs, and lone pairs are electrons that do not get involved in chemical bonding. These lone pairs are sometimes called unshared pairs. I've even seen them called non-bonding pairs. And of course, bonding pairs are the ones that actually get involved in chemical bonds. Bonding pairs sometimes can be called shared pairs. So if you guys are visual, these are going to be your shared pairs, and these are going to be your unshared pairs, okay? All right, moving on to Lewis structures. Basically, Gilbert Lewis was kind of given credit for having discovered the covalent bond, and he does these little dots around the symbols of the atoms, and these dots represent valence electrons. And the nice thing about this is it kind of gives us an idea of how many bonds they will want to form, how many additional electrons they need. And if you know what group an element is in, drawing a dot structure is pretty simple. Now, this is more useful, I think, with covalent bonding than with ionic bonding, but it can be used for both. And there's really two ways to look at this. You can draw Lewis structures for single atoms, or you can draw Lewis structures for molecules. And today our focus is going to be more kind of on individual atoms, and tomorrow our focus will be more on molecules. All right, so real quick about Lewis structures, I'm going to zoom in here. If you know what group an element is in, like lithium, lithium is in group 1. If it's neutral, it gets one valence electron. If you pick an element in group 2, I'll pick calcium. Calcium gets two valence electrons, and those two electrons, they just have to be on different sides. They can't be paired up. Now, we kind of skip over the transition metals. We don't do dot structures for those. But then we get over here to group 13, and I'll choose aluminum. Aluminum has three valence electrons, all of which are unpaired. And here I'm going to change color, because now we kind of get into the non-metals. So I'm going to kind of draw a line here, and on the left side of the line, pretty much your metals. I'm trying to keep it simple, but on the right side of the line are going to be your non-metals. And the one that I can think of in group 14 that you should probably know about is carbon. Carbon has four valence electrons, and I kind of have this expression that singles like to mingle. Carbon can form four covalent bonds, and that could be a combination of single, double, or even triple bonds in some cases. Okay, so the number of singles indicates to me how many bonds it could form. So carbon, four singles, it can form four bonds. Carbon needs four more valence electrons. All right, we get over to group 15, and I'm going to pick nitrogen. Nitrogen has a lone pair, and nitrogen has five valence electrons. Nitrogen has four singles. I'm sorry, nitrogen has three singles, and those three singles can form covalent bonds. So nitrogen has one lone pair sitting on top, sometimes called an unshared pair, and these singles are going to be the one that like to bond. Remember, singles like to mingle. All right, group 16, I'll choose oxygen. Oxygen has two lone pairs and two singles for a total of six valence electrons. Oxygen can form up to two covalent bonds. It could be two singles or a double bond. So two more electrons for elements in group 16 to be like the noble gases, in which case we get to the halogens. Okay, halogens have three lone pairs, three unshared pairs, and one single. And it's that one single that can form a covalent bond. Now I get to group 18, and for the most part, they follow the octet rule. So if I wanted to do neon, neon has all lone pairs. Okay? Neon already has its stable octet, and the exception to that would be helium. Helium having 2 valence electrons, which are paired. So helium only needs 2 electrons to fill up its 1s. So a couple of examples for you guys. We can use dot structures to represent ionic bonds. This is kind of weird because typically we show potassium as having 1 valence electron, and that 1 valence electron gets transferred over to bromine. And even though potassium does have its octet, for some weird reason, we don't actually show it as having an octet, but what we do show is we show pluses and minuses, and we know that opposites attract. Realize that potassium does have a stable octet. It's lost 1 electron, so it's probably going to be like element number 18, but bromine also gains an electron, and by doing so, they become oppositely charged. We don't typically use Lewis structures for ionic bonds as much. All right, so which leads us to hydrogen. Now, a lone hydrogen will have 1 valence electron, and hydrogen would like nothing more than to have a duplet like helium. So the way that we can do that is we can show it as 2 dots. That's a shared pair, or we can draw a single dash. And remember, a single dash represents 2 dots. A single dash represents 2 electrons, okay? All right, so my next example is helium. I kind of already covered it up above. Helium would be a single element with a duplet, so it's kind of the rare exception of when we actually show 2 electrons paired up. Which brings us to fluorine. Fluorine is a halogen, and fluorine would like, well, it has 7 valence electrons if it's neutral, and I can color code those. So maybe these electrons belong to the fluorine on the left. I'll change colors, and these electrons belong to the fluorine on the right. So each fluorine possesses 7 valence electrons, but by sharing a pair in the middle, now they can get an octet to be like the noble gases. One thing you want to think about is when you're doing these Lewis structures for compounds, just kind of think, how many dots should my structure have? Well, fluorine gets 7, the other fluorine gets 7, so all said and done, my final structure should have 14 dots. In the case of the right, just remember, a dash also represents 2 dots, okay? So I think that's the end of my examples today. I think I do have neon on here. We already talked a little bit about neon up above, and tomorrow our focus will be more on molecules. So you kind of got to understand Lewis structures for individual atoms before you start to do molecules, but our focus is mainly going to be on these non-metals, these groups 14 through 18. And I guess we kind of did leave hydrogen out of this. Hydrogen does get 1 valence electron if it's neutral and it's not involved in a bond. All right, guys, you can check out the problems at the bottom of the page. Actually, there are no problems at the bottom of the page. The quiz, the form that I'm giving you today is mostly just kind of review questions. I've left most of the math off of it, so you might want to dig back to some of the stuff from the beginning of the chapter just to kind of freshen up. But we will get a little bit deeper into Lewis structures for molecules next time. I miss you guys. I love you. I'll see you soon.